Welcome students. In our previous class we have discussed about the thermal expansion of solid and liquid. So today we are going to discuss about the expansion of gas. Okay. So we have studied also that in case of expansion of gas there is several number of laws, that Boyle's law, Charles law of pressure, and we know Boyle's law is the volume is proportional to 1 by P when temperature constant. Okay. Temperature and number of molecule we have to keep constant. Okay, so and the volume also, this is called Boyle's law. And in case of Charles law, here pressure is constant and volume is depends on the temperature, means V proportional to the Kelvin temperature. This is your Charles law. In case of Celsius scale, the volume is changes like this equation. Okay, V equals to V naught into 1 plus T by 273. Okay, so uh, V is the volume in at 0 degree centigrade and V is the volume at T degree centigrade. And you can see like the linear expansion or volume expansion of liquid, we have read that V2 equals to V1 into 1 plus gamma delta T. Okay. Here delta T is taken as T because initial temperature is 0 degree centigrade. Okay, and so you can see here that gamma is means coefficient of volume expansion, here 1 by 273, and this is the constant for all gas, all ideal gas also. Okay, and in case of law of pressure, P equals to P naught into 1 plus T by 273. This is called law of pressure. And here also in Kelvin scale, P proportional to Kelvin temperature. And also the gamma P, if I choose in case of Charles law, coefficient of volume expansion gamma V, then in law of pressure, gamma P also here 1 by 273. This is also the same value, then same value and constant for all gas. Okay, so coefficient of volume gamma G always 1 by 273 here. And Avogadro law told that the number of molecule is proportional to V, okay, when pressure and temperature constant. Okay, this is called Avogadro law. And Avogadro defined that 1 mole gas means 6.023 into 10 to the 23 number of molecules. Okay, and now the universal gas law. Universal gas law means, so Boyle provides its law when temperature and number of molecule is constant. Charles provides his law when pressure constant, volume is proportional to temperature. And Avogadro provides its law that when pressure and temperature constant, uh, number of molecule is proportional to volume. If we combine all these law, then we get a universal gas law where all the parameters are variable. Okay. PV equals to nRT. Okay. R is the universal gas constant called 8.31, and N is the number of moles. Okay. And this is the universal gas law. If I tell PV equals to N dash KT, N dash means total number of molecules, and K is the Boltzmann constant. Okay. The relation between K and R is R equals to NK. We have studied also. Now, specific heat of gas. Specific heat. The specific heat we have studied also. The amount of heat required to change or to raise 1 degree centigrade, okay, per unit mass of substance. Okay. So specific heat can be defined as C equals to Q by M delta T. But in case of gas, there is different type of specific heat. One is, if I to call gram specific heat. Gram specific heat means normal specific, like normal specific heat. Amount of energy required per unit mass per unit calorie per gram per degree centigrade. Okay. But in gas, we use basically molar specific heat. So by definition, the molar specific heat means the amount of heat energy required to raise 1 degree centigrade of 1 mole of gas. So here Molar specific heat means 1 mole means m gram. So if C be the gram specific heat, then molar specific heat capital C will be m into mass specific heat, and mass specific heat Q by m into delta T, and m by m is the mass of each molecules, and m is the mass of one molecules, 1 mole gas, and small m is the mass of each gas molecule. So capital M by small m, m is the total mass of gas. M is the total mass of gas, and then that means total mass of gas by molar mass of gas is defined the number of mole. Okay, so then molar specific heat will be amount of energy required per unit mole per unit temperature increment. Okay, so in case of solid, according to Dulong-Pettit law, the all molar specific heat of all metals, only for metals at room temperature, is constant and being nearly equal to 3R. But actually it is not happens. Okay. So but actually the specific heat versus temperature graph is like this. This is not constant. At high temperature specific heat becomes 3R, but low temperature it varies like this. And then Einstein tried to uh, make a different equation to match this graph, but Einstein also failed. Slightly Einstein graph is slightly different than this graph, and Debye taking the electronic specific heat. According to Debye theory, we can get the proper solution of specific heat, and then we get like actual curve. Okay. So specific heat of some metal here given that aluminum 24.4 and copper 24.5, silver 25.5, lead 26.5, like this molar specific heat. Specific heat of water, we know the specific heat of water is 1 calorie per gram per degree centigrade in CGS unit, and in SI unit the specific heat is 4200. Okay, in SI unit specific heat. Thermal capacity means it is defined as amount of heat required to reach temperature of the whole body mass m through 0 degree centigrade to 1 Kelvin, or through 0 degree C, 1 degree C or 1 Kelvin. The thermal capacity is the mass of specific heat capacity, Q by delta. Maybe we can write m into C. Water equivalent is the means equivalent to water. So amount of water which is equivalent to the substance we have taken. Okay, this is called water equivalent. Suppose we have taken some uh, substance which Q amount, H amount of heat is required to reach temperature T degree centigrade, and we have taken some water also. Its temperature, if we want to increase its temperature 1 degree C, we need same H amount of heat. That means this M substance of M mass is equivalent to water of having weight W. Okay, that means the mass of water is the equivalent to this substance. Its CGS unit is gram and SI unit is kilogram of water equivalent. Latent heat is during state change, this heat is absorbed by the substance when the substance change from one state to another state, but temperature will not change. At this condition, the amount of heat required to state change per unit gram is called latent heat. Latent heat of fusion of water about 80 calorie per gram, and latent heat of vaporization of water about 540 calorie per gram. That's all for today's class. Next day we will discuss about calorimetry.